We would proceed in Taylor uh, polynomial expansion, and then we will see Taylor series in multivariable case. Taylor polynomial expansion, Taylor polynomial extension, Taylor polynomial approximation. So these are the concepts that is kind of useful in generic fashion. So it's not a kind of a certain area where we find that these concepts are useful. These are useful in every possible way. One of the most imp- crucial, one of the most crucial development, invention, whatever it is, development, invention, whatever it is that is done in kind of calculus is Taylor series. Marvelous, amazing, that is something which has extreme importance as far as the future of calculus is concerned. So quickly we'll see that what is a Taylor series. If I have a function fx, if I have a function fx, then can I, if there is a function fx, there is a function gx, fx, gx. Gx is exact replica of fx, provided that it is based upon fx only from the derivative perspective. If fx provides derivative information to gx, then gx can replicate fx only based upon the first order, second order, third order, fourth order, fifth order derivative. So there are three steps, three things that we can say, three proof that, but these are the, we would say, three steps that we can proceed upon. So if gx, then we'll see the multivariable case also. If I have a function gx exact replica of fx is master function. Gx is a function which is trying to create replica of fx, where gx gx is only fx gx. Gx is replica of fx, but it is only polynomial, whereas fx can have anything, polynomial, sinusoidal, logarithmic, whatever it is. Gx is exact replica of fx, but it is only set of polynomials. So question arises is, can I have a function gx which is replica of fx, but this is only polynomial function, x to the power 0, x to the power 1 plus x to the power 2 plus x to the power 3 plus x to the power n, only polynomial. Gx is only polynomial. If gx is only polynomial where fx is everything algebraic, then can fx be represented as a set of polynomial algebraic equation? So that is the idea. Now consider fx is fx is fx is x to the power 0, k x to the power 0. Then can I replicate in gx? Yes, k, just copy it because both are kind of, it is copied. So you can say, can you give me something with zero derivative? Then k, leave it, k, I just started. Anyway, fx has a function, suppose fx has a function of order 1, only one function, that is kx. Now, can fx be replicated in gx in polynomial way? Now, gx is asking fx to give the first order derivative, and fx is kx. First order derivative is k. Then here it will say k, that is dy by dx, dfx by dx, first order derivative, dfx by dx into x, then kx, replicated. If fx is kx and first derivative is being passed to gx, and that is k, it quickly replicated as k dfx by dx into x, first order derivative. Now fx is second order polynomial equation. So I would say kx square, kx square. Now gx is asking for second order derivative. If that is the case, then it is k into 2. Okay, so k into 2 into 1. That's it. K, first order derivative is 2, then again derivative 1. X value k into 2 into 1. It passed k into 2 into 1. Now it wrote d2 fx by dx square x to the power 2 divided by factorial of 2, because factorial of 2 is coming as extra. So it is k into 2 into 1 x square divided by factorial of 2. Net is k x square. Replicate it. Now fx is power of 3. Okay, so fx is power of 3, k x to the power 3. So k into 3 into 2 into 1, triple order differentiation. Now it is passed to gx. Gx is saying d3 fx by dx cube x to the power 3 by factorial of 3. So d3 fx by dx cube is nothing but k into 3 into 2 into 1, then x to the power 3 divided by factorial of 3. Factorial of 3 gone. Then it is k. K into x to the power 3. Exact replica of fx. If this is the case, then it looks like if I sum up everything what we have done, then I have full set of a polynomial equation in gx. That is nothing but that is nothing but gx equal to f at, okay, let's leave the first term constant. Gx equal to dfx by dx x plus d2fx by dx x square by 2 plus d3fx by dx x to the power d3f d2 d2fx by dx square fx by factorial of 2 plus d3fx by dx cube x to the power 3 by factorial of 3 plus so and so plus x to the power n plus x to the power dn fx by dx to the power n x to the power n by factorial of n. If I add everything, then gx is nothing but set of full polynomial. We can say that represent fx provided fx has everything. Full polynomial, sinusoidal, whatever. Because gx and fx, gx is exact replica of fx as far as only polynomial equation is concerned, but gx wants fx from fx only the derivative, and it arranges everything in a polynomial way. Now if gx is nothing but kind of a polynomial approximation, polynomial equivalent of fx, then for any line, if it is passing through a point a comma b, if any line is passing through point a comma b, then equation will change. So gx equal to f at a, y minus y0 equal to dy by dx x minus x0. So that is the concept of any line when it passes through point x0, y0. So y equal to y0 plus dy by dx x minus x0. Similarly, gx equal to f at a, that is y0, f at a plus dfx by dx at x at a, x minus a plus d2fx by dx square at x at a, x minus a whole square divided by factorial of 2 plus dnfx n by dx to the power n x at a, x minus a to the power n divided by factorial of n. So now we have full-fledged approximation. Taylor series, this is our proof. Anyway, Taylor series approximation for any function fx. So gx equal to fa plus dfx by dx x minus a plus d2fx by dx square x minus a whole square by factorial of 2 plus d3fx by dx cube x minus a to the power 3 by factorial of 3 plus d dfxn by dxn x to the power n by factorial of n. So this is the Taylor series full polynomial approximation of any function f. Now it can be sinusoidal, logarithmic, whatever it is. We are interested in derivatives. So if derivative is provided, we can create gx that is polynomial approximation of any function fx. So what we saw here? We saw that we can create the carbon copy of fx in gx as polynomial express approximation if I get the derivative. And this is the way we have to arrange the derivative. Another proof came here is consider that fx is polynomial equation. Fx is full-fledged polynomial equation. Then what would be gx? Exact replica. So fx equal to fa plus fa plus x minus a plus x minus a whole square plus x minus a to the power 3 plus x minus a to the power 4 plus x minus a to the power n. Now can you replicate as far as derivative is concerned? So now gx who wants to replicate fx when fx is polynomial, now gx is saying give me the first constant, that is fa, means zero order derivative. So fa is given, now gx equal to fa. Now give me the first order derivative when x equal to a. So first order derivative, then fx equal to fa plus x minus a. Fa gone, and x minus a derivative, it becomes 1. 1 is given here. Then it becomes gx equal to fa plus dfx by dx is 1 x by factorial of 1. This is what we have arranged now. This is what we see. The way we were taking one by one, you remember little back, we were taking x, then x square, then x3 and trying to create the replica. So this is the way we have found. Now what about the other term? Fx is fa plus x minus a whole square. If I take single derivative, fa is gone, x minus a become 1, but others remains. So those are also coming in first order derivative. But what about when x is a? When x is a, then all become 0. At that moment only 1 comes into the picture. Now second order derivative, fa x minus a gone, x minus a whole square, it becomes 2 into 1. 2 into 1 is passed here, and then it becomes fa plus dfx by dx, that is 1 x minus a, plus now d2fx by dx square, that is 2 into x minus a whole square by factorial of 2. 2 cut down. So x minus a whole square. Exact replica we are getting. Now third order derivative. fa gone, x minus a gone, x minus a whole square gone, x minus a power 3, third order derivative becomes 3 into 2 into 1. And then at x equal to a, rest becomes 0. So 3 into 2 into 1 passed here. So fa x minus a whole square plus now d3fx by dx square, x minus a to the power 3 by factorial of 3. 3 factorial cut down, x minus a to the power 3. So this way also we can prove that at point x equal to a, we can replicate fx as gx, where gx is fa plus dfx by dx x minus a plus d2fx by dx square, x minus a whole square by factorial of 2 plus d3fx by dx square, x minus a power 3 by factorial of 3 plus dn fx by dxn, x minus a to the power n by factorial of n. So this is the second proof we saw as far as Taylor series is concerned. What about the third proof? The third proof is integration by part. Okay, integration by part starts from difference chain rule of the differentiation, or the product differentiation of product of two functions. If I have a function fx and gx, and there is an algebraic equation that is fx into gx, then what is differentiation of it? That is nothing but fx differentiation of gx plus gx differentiation of fx. So someone can prove it. I am not going to prove it right now, but someone can prove it through first principle also, delta x way, or through chain rule, or through other way that we will show now. So now if I have fx into gx equal to fx differentiation of gx, fx differentiation of gx plus gx differentiation of fx. What about fx differentiation of gx? fx differentiation of gx. fx differentiation of gx equal to fx into gx minus gx differentiation of fx. fx gx, fx into gx differentiation of fx into gx equal to fx fx dgx plus gx dfx. So if I just keep it fx dgx equal to, then this will go this side, and we have d of fx gx minus minus gx d of fx. If I work more on it little bit, then it will become the integration of fx gx, integration of fx gx. Right now we have fx d of gx, fx d of gx equal to dfx gx, dfx gx minus gx dfx. Okay, if I consider that fx gx, d of fx gx, if I calculate the integration, then it becomes d of fx and gx become fx and gx, fx and gx. Okay, now if I consider gx as derivative of something, already it is derivative of something, then it becomes integration sign. Then fx gx integration will become this side, it will become fx integration of gx minus big integration differentiation of fx and then gx integration of gx. Someone can try it. I am not here to prove it. Means it is one step only. So it is also called chain rule in differentiation becomes integration by part or chain rule in integration. What is chain rule in integration? Chain rule in integration is if I am trying to integrate multiplication of two functions, fx gx, integration of fx gx dx, fx gx dx, that is the integration, equal to fx integration of gx minus big integration, first differentiation of fx and then integration of gx, whatever it comes, then full integration. So this arrived from derivation of fx and gx only. So from there, step by step, we come to this stage. Now let's consider that we have fx as a function. Now we are rewriting fx. fx is a polynomial function. Fx is an algebraic function, polynomial plus sinusoidal, trigonometric and logarithmic and so many. That is the fx. We are rewriting fx again based upon the only the derivative I receive from the fx, what it would be. Now if I say integration of derivative of ft dt, derivative of ft means dft by dt, dft by dt, that is derivative of ft. If I calculate integration of that from a to b with dt, it becomes fb minus fa. So that becomes the integration of dft by dt with dt becomes ft. Integration of ft dt is integration of ft, another function gt. But integration of dft by dt with dt becomes ft. Limit is a to b, then fb minus fa. So fb minus fa equal to integration of ft dft by dt, dt from a to b. Same thing. Now fb equal to fa, fa we take that side, fb equal to fa plus now integration of dft by dt, dt from a to b. We can write in this fashion. So now let's take the chain rule in calculating the dft by dt, dt integration from a to b. dft by dt can be written as dft by dt into 1. Anything we can multiply by 1. dft by dt into 1 dt. So I have full expression as fb. F is a function and inside braces b, function over independent variable b. fb equal to fa braces fa plus integration from a to b dft by dt into 1 dt. Now dft by dt is one function, one is another function, the that is the integration we have to calculate. One we can say t to the power 0 also. Okay, so now if we calculate the integration, so t to the power 0 dft by dt into 1 means dft by dt into t to the power 0. I replace t with t minus b. It's possible. If t equal to t minus b, if I keep it, okay, then dt will remain as it is because differentiation is same thing. Or we can say t equal to x minus b. Then it becomes then fx dft by dt or f single quote t f single quote x minus b dx, whatever. Now let's keep as t only. So dft by dt into t minus b power 0, that is 1 only, dt. If I do integration by part, then it becomes dft by dt, that is single derivative of ft, dft by dt, and then integration of t minus b to the power 0, that is t minus b. Lower limit is a and higher limit is b. Then b if I keep, then it becomes 0. Then a I keep, then it becomes a minus b. Minus is there because a lower limit, so it becomes b minus a. And then this is first of the part by part of chain rule in the integration. Then minus bigger integration from a to b, and we have dft by dt. It becomes again one derivative d2ft by dt, d2ft by dt into the integration of t minus b of 0, that is t minus b. Now full expression is fb equal to fa plus dft by dt b minus a, okay, where t is t dft by dt at t equal to b. So I can say dfb by dt or dft by dt where t equal to b, t equal to a, at t equal to a. Then braces b minus a minus, and then integration a to b d2ft by dt square into t minus b power 1. Now if I integrate this again by part, so if I integrate d2ft by dt t minus b dt a to b, now let's take as integration by part. So d2ft by dt square will remain, and t minus b integration will be t minus b to the power 2 by 2. If I place limit a to b, b means full 0. If I shift a there, then a minus b whole square. That is same as b minus b, b minus a whole square. A is lower limit and outside it is minus, so minus minus gone. Okay, now then minus big limit from a to b, now again one derivative of d2ft by dt square, so it becomes d3ft by dt cube into x minus t whole square by 2 dt. So this will result into fb equal to fa plus dft by dt x b minus a plus d2ft by dt square b minus a whole square divided by 2 minus then from a to b d3ft by dt cube. Can you see the way it is growing? X minus a x t minus a whole square by 2 dt. If I do go for partial derivative integration again, then integration from a to b d3ft by dt cube t minus b t minus a to the power 2 dt will become t minus a to the power 3 divided by 3 into 2. By 2 is anyway there, 3 into 2. If I set a to b, b means full 0. If I place a, then it becomes a minus b to the power 3 or minus b minus a to the power 3. Minus minus, if you settle down, it will become positive 1. Then minus again a to b d4 ft by dt4 t minus a to the power 3 by 3 into 2 dt, full integration. If I see this for the nth, then it becomes fb equal to fa plus dft by dt x b minus a plus d2 ft by dt square b minus a whole square by factorial of 2 plus d3 ft by dt cube b minus a to the power 3 by factorial of 3 plus d4 ft by dt4 b minus 4 to the power 4 by factorial of 4 plus dfn 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 t by d to dt to the power n t minus b to the b minus a to the power n divided by factorial of n. If I replace b with x, if I replace with x, b with x, then fx, we are rewriting fx. Now the new fx, that is Taylor series, which is only in polynomial way, the new fx is fx equal to fa at a plus dft by dt x minus a plus d2 ft by dt square x minus a whole square by factorial of 2 plus d3 ft by dt cube x minus a to the power 3 by factorial of 3 plus dn ft by dt to the power n x minus a to the power n divided by factorial of n. So this is the Taylor series, third proof of the Taylor series. So we have three proof of the Taylor series. Probably you will not find anywhere else because we have done the first proof from our own. Two proof you may get. So this is three-way proving the Taylor series. Let's prove the Taylor series for the multivariable case. This is what is awaited. Okay, so multivariable case, what is the equation if I see the plane? What is the equation of a line? The line equation is y equal to dy by dx into x. If I have rate of change along x-axis, multiplying by any x gives me y at that point. If I have x-axis and if I know dy by dx means how much y changes if there is unit change along x-axis, that is dy by dx. If I know the rate of change, that is dy by dx, at any point x on x-axis, what is the y? That is y equal to dy by dx into x. So dy by dx into x. If dy by dx is an algebraic equation, then if I am trying to find what is y at x0, any point x0, then dy by dx at x0 into x0. That is the y0 we can say. Similarly, for the 3D, where we have independent component is not x-axis, independent component is full-fledged xy plane. If independent component is xy plane, then the height, earlier the height was y and independent component was x-axis. Now height is fxy, not fxy. Where independent component is xy plane, then height is fxy. If height is fxy and independent, that is dependent, that is z, then an independent component is xy plane, then what is relationship between fxy and fxy, that is z, and x and y? Earlier in two-dimensional, y or fx equal to dy by dx or dfx by dx into x. What is here? Now consider that this is x-axis, this is x-axis, this is parallel to x-axis, this is y-axis, this is origin. this is origin, this is origin, and this is y-axis. Then this is x-axis, this is parallel to y-axis, this is parallel to x-axis, this is xy plane. Let's keep y-axis constant and then make the x-axis down. Now there is certainly, if I say this is z-axis or fxy, what is dfxy by dy? If there is a rate of change in the, consider the z is how much change in z we are seeing. If I am the x-axis, I am tilting like this. Okay, what is z at any point? That is the question. What is z at any point? Or someone can say what is change in the z, whatever it is. Now consider this is xy plane. Keeping y as constant, now I kind of tilted the x-axis. If that is the case, then if this was z, then z went down. If this is the line, if this is the equation of a line and vertical is z, then equation of a line is nothing but dz by dx. What the way rate of change that is seen in z as per the variation in x into the x at any point x, at any point x. So consider this is xy plane. I am not shifting the xy plane. Xy plane cannot be shifted. So this is xy plane. I have a surface like this. This is xy plane. And I have a surface like this where the y-axis of the surface is intact at the y-axis only, but x line x is down. It is in negative side. This is xy plane. This is origin. This is y-axis. This is x-axis. What is z at any point x? What is z at any point x? What is z at any point x? What is z? Then what is dz by dx? What is the variation in z I see as per the variation, unit variation in x, dz by dx? If I know dz by dx at any point x, dz by dx into x gives me this height. Okay, now the idea is on the surface, if this is xy plane on surface, now this is the surface, this is xy plane, this is xy plane, and this is the surface. At any point x comma y, what is z? That is the question. It is understandable. If I have xy plane, if I have xy plane, if I have xy plane and there is a surface like this, then on xy plane I have many set of x comma y points. Many points are there in the xy plane. At any point x comma y, what is z? At any point x comma y, what is z? Okay, so if surface is like this, then any point x comma y for the x direction, whatever is the dz by dx, whatever is dz by dx into x, give me the fxy. Okay, what about this is the z we are getting, but wait, this is not the end. Now keeping this surface, this line, this surface, this part constant, I am shifting y like this. Then at this is the surface. Actual xy plane is like this only. This is xy plane, but surface, any surface, third party surface. So I shifted it like this, and then asking at any point, this is xy plane, at any xy plane, any x comma y, what is the z? At any x comma y, dz by dx, slope in x-axis into the x is the fxy. One thing. Then keeping this line constant, I am now shifting like this. Now what is fxy? If this is xy plane at some xy, x comma y, what is the fxy? So first we have to see the slope along x-axis multiply by x. So z is down now. At that point, the point where I am calculating the z, z is down now. Okay, if there is no change in the y, but if y is, Keeping this line constant, now if I am changing the y, then at that point z shifted little bit. Can you see this clearly? If this is xy plane and I had a surface on the xy plane, now surface, keeping the y constant, surface is tilting like this, then there is dz by dx, height is dz. So at any point, if surface is at xy plane, if I don't have two surfaces, consider this is xy plane. If this is xy plane and this is the surface, both are at same location. Now xy plane is at same position, but surface is tilted like this. So xy plane is there only, but surface is like this. So when this is xy plane and surface is at xy plane, then at any point x comma y, what is the height? 0. Everywhere 0, because surface is exactly matching the xy plane. If I have a 3D surface that is a flat surface, consider these two are not there. Consider a flat surface, and this flat surface is kept on the xy plane. That any point x y, the height is fxy is 0. Now this surface I am tilting like this, keeping this constant. If that is the case, then what at any point x comma y, what is the z? Fxy. What is the z? Z is nothing but whatever the rate of change dz by dx we are seeing, because change has made only in the x direction. Y direction is constant. So dz by dx, so if this is the x comma y, then this is x, and from origin this is y. If this is the origin, then this is x and this is y. This is x comma y. Dz by dx into x is the height. So this is the at any x comma y, what is fxy or d or z? That is nothing but dz by dx into x. But hold on. Now this is the point that I am aiming. If this is the point I am aiming, what is fxy? Now keeping the y constant, keeping this constant, y I am shifting. Can you see this point is going up? Earlier it was at xy plane. This point came down. So dz by dx into x. That is the now new position of this point. Now, if I rotate, keeping this constant, if I rotate like this, then this point came up. How much it came up? That is nothing but dz by dy into y. So, net height, if I calculate, the new z is dz by dx into x plus dz by dy into y. So, the fxy, if I have any polynomial, any function fxy, if I want the first order approximation in polynomial, then fxy is nothing but dfx by dx into x plus dfx by dy into y. Can we see this? So in line equation, for any fx, if I want the polynomial approximation in first order, then it is fx gx equal to dfx by dx into x. If I have any fx as algebraic equation in multivariable case x comma y, so I have fx comma y, not fx comma y, any equation, then here the first order derivative equivalent is gxy equal to dfxy by dfxy by dx into x plus dfxy by dy into y. So this is, now we understood that this is basic. So any invention happens on top of basic. So this is what we understood, that this is what is going to happen. Now let's proceed in the multivariable case. Multivariable case, it is foolishness to consider there is two axes x and y as independent. This is what we are saying. Clever step is consider x-axis and y-axis, that is xy plane, as single independent component. So I have z, that is fxy. Fxy is dependent component then independent component is xy plane, not x-axis and y-axis. Okay, so that is xy plane. If it is xy plane, if xy plane is the independent component, then what is xy plane? If it is x-axis, then it is x. If independent component is only x or x-axis, then it is x. If it is independent component are two, x-axis and y-axis, then it is x comma y. But I don't want this. I want xy plane being independent component. Okay. If that is the case, now consider the kind of line equation. For line equation 2D. So line equation is nothing but fx equal to or gx equal to dfx by dx into x. But in multivariable case, gfxy, gxy, gx equal to dfx by dx into x. For single order, here gx comma y equal to dfxy by dx into x plus dfxy by dy into y. Okay. Now these are something that is now related to each other. Single dimension gx equal to dfx by dx into x. Two dimension gxy equal to dfxy by dx into x plus dfxy by dy into y. Now we have to find xy independent component through these two. Now let's go back and see the actual polynomial let's the way we started our own proof. You remember the first proof we gave in Taylor series. Now consider that fx is a polynomial equation for which I have to find mirror equation as gx. I am sorry, fxy is the polynomial equation for which I have to find mirror or approximation polynomial equation as gxy, from fxy to gxy, where fxy is first order polynomial. First order polynomial means it is x plus y. Consider it is x plus y. Fxy equal to x plus y. Okay, if it is x plus y, if I go with the single derivative along x-axis, it becomes 1. Y is gone. If I go single derivative along y-axis, then x is gone and it is y. Y is 1. Okay, so single derivative along x-axis, that is 1, and single derivative along y-axis, that is 1. So if gx is trying to replicate fx, when fxy equal to gxy is trying to replicate fxy, where fxy equal to x plus 1, then gxy would ask dfxy by dx and dfxy by dy. If it is passes to it, then it can create as dfxy by dx into x plus dfxy by dy into y. Why it is doing like this is because it is already proved. I would rather say, can we go reverse fashion? If gxy, for multivariable case, if gxy, replica of fxy is gxy, if gxy for the single order derivative is dfxy by dx into x plus dfxy by dy into y, gxy for the single order derivative or single order polynomial, gxy equal to dfxy by dx into x plus dfxy by dy into y. If that is the case, what it needs from the fxy to generate this? But this is proved one. If proved one, then it needs dfxy by dy and dfxy by dx and dfxy by dy. Now it is asking fxy, can you give me dfxy by dx and dfxy by dy, where both are 1? If that is the case, then fxy is saying it is only possible I can give you dfxy by dx as 1 and dfxy by dy as 1 when fxy equal to x plus 1, x plus y. If fxy equal to x plus y, then equivalent is equivalent in gxy is dfxy by dx into x plus dfxy by dy into y, then this proves that for x plus 1, if fxy equal to x plus 1, the equivalent is dfxy by dx into x plus dfxy by dy into y. This is the basic polynomial, basic multivariable Taylor series for the power 1 we got. But it is exact replica of single variable. Multivariable, we got it. Multivariable, if fxy equal to x plus 1, then gxy equal to dfxy by dx into x plus dfxy by dy into y. We proved this through other way. But anyway, but this is exact replica of single variable case where fx equal to x, then gx equal to dy by dx into x. If that is the case, then this proves that the x if independent variable is 1, that is x-axis, then in multivariable case when independent variable is a xy plane, then equivalent of x is x plus y. If x plus y, if x represent x-axis in 2D, then in 3D, x plus y represent xy plane. If that is the case, then we can proceed from fxy to gxy as far as polynomial approximation is the case. Now, fxy, the first order anyway we have calculated. Let's try with the second order. So fxy, only second order. Second order is not nothing but x plus y whole square. X plus y whole square. Earlier we started with x square, x to the power 3. Now we started with x plus y power 1. Now it is x plus y to the power 2. So that results in x square plus 2xy plus y square. If that is the case, then dfxy by dx square, that becomes 2. Others gone. dfx d2fx by dy square, then y square becomes 2. Other gone. Now dfxy by dx into dfxy by dy becomes 2. That is 2xy. X square plus 2xy plus y square, then x square gone. If I say dfxy by dx and then dfxy by dy, x square gone, y square gone. 2xy is now 2. So that derivative will be passed to gxy. Now gxy, because gxy has to calculate the exact replica of x plus y whole square. So exact replica would be d2fxy by dx, d2fxy by dx square into x square divided by factorial of 2 plus dfxy by dx into dfxy by dy, because 2 is anyway 2 was there and 2 is coming here, so there is no invention here, plus d2fxy by dy whole square divided by factorial of 2. If I take in same version, let's see x plus y to the power 3, third order polynomial if fxy is. Now how we can create gxy as exact replica? Then x plus y to the power 3 would become x to the power 3 plus 2x square y plus 2xy square plus y to the power 3. If that is the case, then whole derivative it will provide. One is d3fxy by dx cube, one is d3fxy by dy cube, one is d2fxy by dx square and multiplied by dfxy by dy. One it will supply dfxy by dx into d2fxy by dy square. If whole type of derivative it provides, then exact replica can be created as d3fxy by dx cube into x to the power 3 divided by factorial of 3 plus I believe it is 3, consider it is as 2xy only. I don't remember much now, but it will be d3fxy by dx cube into x to the power 3 d3fxy by dx cube x to the power 3 divided by factorial of 3 plus d2fxy by dx square into dfxy by dy plus dfxy by dx into d2fxy by dy whole square, okay, divided by 2, because x square become 2 divided by 2 plus d everywhere 2. So I will rephrase it. So third order becomes gxy equal to d3fxy by dx cube into x to the power 3 by factorial of 3 plus d2fxy by dx square by 2 into dfxy by dy plus dfxy by dx into d2fxy by dy square divided by 2 plus d3fxy by dx to the power 3 divided by fact d3fxy by dy cube into y to the power 3 divided by factorial of 3. Keep doing like this. And then you just imagine what will happen to the t to the power n, x to the power n. X to the power n d to the power 3 d to the power n fxy by dx to the power n into x to the power n divided by factorial of 3 plus in between whatever you see plus at the end d to the power n and f y divided by d y to the power n into y to the power n divided by factorial of n. So this is something that is multivariable case. Now anyone is free for the more. We started with single variable, multivariate. Then in multivariate we have taken xy only. Someone can start xyz, xyz alpha and whatever in similar fashion. We will do it. So we will try with XYZ also. Then we will proceed in Maclaurin for this and then example on it. So that we will do.